Okay, so Joe Ayers, I think hopefully many of you know me from interacting with you in the forums, and Randy introduced me a little bit earlier on some of the contributions. I have a presentation here. We're gonna stretch our minds a little bit, dive into some of the communication theory. I think, really to understand some of this takes a lot of digging through the mathematical descriptions of this to really understand it all. And we're not going to do that here today. We're going to keep it at a higher level, but look at essentially the communication theory of what an 802.11 signal is, so that we can better understand it and know how we can optimize our sites and links to maximize the data throughput on it. So we're going to start out with just the basics here. Something that we should hopefully all be familiar with some of our Part 97 exams. It may have been a while for some of you on taking some of the theory, but we're going to start out with just a basic carrier wave and how the data is modulated on it for digital communications, and then expand that into what the OFDM signals look like and why we do that, and what's the benefits of that. Touch base on what MIMO is, how that adds more complexity to it. Touch base on these rates that AREDN devices use, their 802.11n specification. And then look at how the radio is choosing these rates in putting it all together. So I'm going to try to keep one eye on the questions. So if you do have questions, pop them up, and I'll try to answer them in real time just the same. So let's take a look at a way of modulating digital information on a carrier wave. So this bottom line here is what the signal, a representation of the carrier wave, looks like, and it's a sinusoidal wave at a given frequency. And down here we have from 0 to TS, and that's the symbol length of time that one, in this case 2 bits, 1 1, are transmitted during that time. And then we look over here between to T to 2T, there's another symbol or another set of 2 bits that are transmitted by that carrier wave. And so what are we doing here? This is a quadrature phase shift keying. We're changing the timing of that carrier wave. And so you can see here in the first symbol that's being transmitted, we're just holding that carrier wave with the timing of it starting, and you can see it's kind of at the top of the sine wave here, and starting at the top, and we hold it for that period of time. Look at this second period of time where we're transmitting and we've changed it. See where it starts in the timing of that carrier wave. It's about 25% of the way through the timing of the first symbol. And then let's jump out here to the fourth one. This one is starting at the top. It's about 50% of the way through the timing of the first symbol. And then this third one here is actually starting down here at the bottom. It's about 70%, 75% of the timing of the first one. So quadrature, we've divided up the timing of that carrier wave into 4 discrete, starting at the top, 25%, 50, 75%. And we've have 4 states of this carrier wave, all based on the timing. Now note, with quadrature phase shifts keying, we're just changing the timing of the signal to communicate ones and zeros, 4 discrete positions of the signal. We're not modifying the amplitude. We just need enough power to have significant signal to noise ratio to be able to receive and detect it. Quadrature, there's 4 timing symbols, and I talked about this already. So got that. Now up here at the top is another mathematical way of representing this signal we call I's and Q's, and I'm not going to go into that, what that in detail. That's something you might want to look at offline, but it's just a different mathematical way of describing this signal. Quadrature and amplitude, it's Cartesian mathematical representation. So the key idea here is here's a carrier wave. The timing of it during very specific intervals, the timing of it tells us what symbol is being transmitted, and the receiver is just figuring out where the timing or phase of that carrier wave to pull out and detect what those bits are. So let's move on and make it a little more complicated here now. So I'm just showing here that I and Q mathematical representation, but it's still a carrier wave. And this is the quadrature amplitude modulation scheme of modulating information. Well, we're gonna now hold that signal into 16 different states, discrete states, and so we call this representation here, we call it 16 QAM, and with that we're transmitting 4 bits for each position of the signal. So we're just increasing the amplitude, or of the signal up and down into 4 states, and we're have 4 states of the timing to then encode these bits. So with more positions of the signal that we're trying to detect in the receiver, we're going to need a little higher signal to noise ratio to make sure that we're getting the right signal state. It needs more, that additional strength to detect all of these different 16 positions. So 16 up to 64, and it could be even more in the AC specification. That's going up even higher than 64. We'll see the 802.11n, but you'll see as they keep developing these standards and improving them, they keep making them more complex, more complex, and more rate and more efficiency of the channel in transmitting. Okay, so let's talk about, we have a carrier wave. We're transmitting digital, it's put into specific states by timing phase or by amplitude, and it's giving, it's giving us that information across the channel in those discrete states. So we could design this communication system and just have one carrier wave in 20 megahertz channel. And if we did that, we would have to transmit, in the symbol time would be 64th the time, compared to if we had 64 carrier waves right next to each other in the bandwidth, because then we can transmit each carrier wave in parallel and take up the full timing comparatively. So so this one wave, with that limited time to transmit each symbol, it has an issue where this is where the fading or reflection paths of signals come into play. So let's look at this chart here on the left. In 802.11 specifications, the symbol timing actually includes the guard channel or guard interval up front. So this is the receiver's perspective. So if I'm here at the receiver and I start transmitting and I receive the direct signal, and here's the time that that symbol is transmitted, 4,000 nanoseconds. And then I get a reflection path that's slightly delayed. It's starting to push out into the guard interval of the next symbol over here. And maybe I have another reflection path and it's pushing out and fully consuming that next guard interval for the next symbol. If I had 64th the time and I had one carrier wave trying to transmit the same number of bits, I don't have enough time here in that guard interval such that this symbol is now pushing into the next direct path symbol that's being transmitted and trashing it, called inter-symbol interference. And so there's only so much rate I can get with one carrier wave because the timing has to be enough between the symbols to not trash one another with these reflections or this fading occurring. So there's also a concept of selective fading, where in that 20 megahertz bandwidth, the environment might have reflections only in a particular 3 megahertz section of that 20 megahertz. So with one carrier wave, now that selective fading in one area has trashed that symbol, and I'm not gonna be able to detect that symbol and that data coming across. But with many carrier waves in the bandwidth, only some of those carrier waves are affected, and there is forward error correction bits that are spread across all the carrier waves, such that the receiver, although it doesn't get one or more carrier waves and can't detect them, the data that it does receive on the other carrier waves allows it to recover, the forward error correction. So we can recover that data without having to retransmit it. And then the other benefit of OFDM is that, well, this is actually the negative that has to be worked around with OFDM, is that with one carrier wave, it's relatively a low peak to average signal ratio. The envelope of that energy, it has the peak and the average signal are fairly low, and what that means is that the power amplifier, if it has a high peak to average signal power ratio, it means that the power amp can get saturated more easily or go out of linearity. So therefore, we start getting a loss of signal quality, we start getting out of band emissions, and we get data loss. So we have to be careful on the power and this high peak to average ratio going through the power amp on the AREDN and 802.11 specification signals. I'll talk about that here in a little bit some more. Another very interesting thing about how a symbol is transmitted is this end signal, 800, the guard interval time, the very end of what's transmitted is copied and transmitted intending to be in the guard channel area. And what that does is it's a one-tap equalization. We're transmitting the same signal twice so that the receiver can use that to maximize its ability to detect what the symbol is. So it has this form of equalization built into it that some may be familiar with analog equivalent, where similar things are done. The same portion of the signal is transmitted twice. Okay, so mini carrier. Key idea here is we're doing mini carrier waves. Each carrier wave takes on a much longer time to transmit the symbol than if we were trying to send all the same data on one carrier wave. And that helps us to mitigate or make fading and reflections a non-issue. Okay, moving along here. So let's look at what is the O, FDM, frequency division multiplexing. That's the mini carrier wave idea. Let's look at the O in OFDM. That means orthogonal carrier waves. Now, what's orthogonal mean? It means uncorrelated. It means they don't overlap. It means that on the receiver, we can uniquely detect the carrier wave. We don't have inter carrier wave or inter symbol across the bandwidth interference from one another. So there's a real key criteria here to have a signal orthogonal for these digital signals. The spacing of the carriers must be this relationship, and T is the time that we're transmitting the symbol. So the time we transmit this carrier wave and how long we transmit it impacts what this looks like in the frequency spectrum of where the energy across that spectrum is showing up. So when we space these carrier waves to be 1 over T of the symbol time, you can see here's a carrier wave, and that its energy over in this frequency area, there's a null at the center of the next carrier wave. So we're not interfering with that right at the center where that null is. So I can detect that, and it's uncorrelated or orthogonal from the adjacent carrier waves. So there's no guard area. They're just engineeringly designed to have these nulls here. So across these carrier waves with 64 carrier waves, if we looked at 802.11ag, the specs keep evolving compared to 802.11n. They keep packing more data rates in, and even AC goes even further in packing in the data rates with higher QAM rates, which of course require higher signal to noise ratio. But so if you look here at the 802.11ag, now this would be your Linksys devices, where these devices are only doing 802.11 A or G. Now, one of those is the 5 gigahertz specification, the other is the 2 gigahertz specification. There's 52 subcarriers, of which 48 are having data. There's 4 pilot subcarriers, but there's a total of 64. So if you took this spacing times 64, you'd end up with 20 megahertz. Now there's 52 subcarriers, 48 containing data. There's people that do entire PhD theses and studies about how to modulate all of these carriers to optimize the signal and maximize throughput. So some of those subcarriers are modulated in a way to, for example, minimize the peak to average power ratio of the signal. They're designed in such a way to optimize the signal so that it minimizes interference with adjacent 802.11 signals, so that it minimizes inter-symbol interference, both across time and transmitting the next symbol, and inter-carrier wave interference. So it's a lot of smarts. So we could take a whole session and dive into how all of these subcarriers are modulated to optimize it. So with 802.11n, it jumped up to 52 data carriers, and then there's some that are null. I think it's the very center ones are just a null carrier wave. There's several pilots that are proportionally spread out through the band. The pilot carrier waves help the radio to synchronize on to and detect it, the signal. So an incredible amount of smarts in the engineering behind all of this, and it just gets more and more complex with each of the specifications. So orthogonal, key idea here is they're orthogonal. We can pack in all of these carrier waves carrying digital data, all in very, very close proximity, and we can still, on the receiver, detect all of the state of those carrier waves to pull out the symbol, which could be 2 bits, 4 bits, 6 bits on each symbol that each carrier wave is transmitting. So let's kind of put it together on what that signal looks like now. Here would be showing, there's 64 carrier waves, each modulating, and when we transmit a symbol, of course, all the carrier waves are doing the same, 16 QAM or a quadrature, just phase time shifting in 2 bits, but they're all using the same scheme across that bandwidth, and they're transmitting. So the symbol, which includes that guard interval, is transmitted over time. So we're seeing the time come out this way, and we just transmit successively all of the data to send it across. Now, I don't dive into it here into this presentation, but there's a entirely another complex mechanism as to how the data is interleaved or put on those carrier waves, so that if you lose any of the data on one character wave, the forward error correction codes will recover it, so that we maximize the ability to recover the data if there's any selective fading, and the error correction scheming that is used. So a whole lot more complexity on top of it that we won't get into, of just how the ones and zeros in the data is spread across each of these symbols. So one thing to keep in mind for our use is that we often go from a 20 megahertz to a 10 megahertz or even a 5 megahertz channel. So what's happening here? We're still going to have 64 carrier waves. This is a digital DSP. We're doing fast Fourier transfers. These are digital, and they're based on, to do them very efficiently in the chipset, to do these mathematical conversions from frequency to time domain. We have a chipset that's based on an order of 2. So we need to do an FFT that's 64 bits, or in other words, 64 carrier waves. To do that, if we wanted to go to the next level, we'd need to do it efficiently in the chipset. We'd need 128-bit FFT process. So hence 64 character wave, 64-bit FFTs and going on to convert from time to frequency domain, mathematically as how the signal is represented. So for us, when we go to 10 megahertz, well, go back to that orthogonality to keep that signal so that we don't trash, but each carrier waves aren't trashing one another. We have to double the symbol length to squeeze it in half of the bandwidth. And so when we go to 10 megahertz, we went from a maximum data throughput of around 144 bits per second to 72 or so bits per second, because now we're taking up twice the time to transmit the symbols. And then 5 megahertz does that again. It doubles that. But also, if you think about it, when we double that symbol timing, our guard gap is twice. It's no longer 800 nanoseconds, it's now 1600. We have more room for reflections and fading. We can, at longer distance, we need that longer room as there's more time and distance for a reflected signal to travel. And so we need that extra time so that we're not getting those symbols trashed from one symbol to the next. So 20 megahertz with the shorter symbol time will only go so far. And I forget offhand, I think Randy showed a slide earlier, the maximum is 29, 20 some miles. But as we go to 10 megahertz, then that is gonna double or plus or minus, and 5 megahertz even farther than that. So these that's why we can see when we go to longer distances, one of the reasons why 10 megahertz has a more optimal channel than 20 megahertz, because we'll start pushing into where the symbols will start trashing the successive symbol at 20 megahertz. There's just not enough guard gap space there for it. Okay, so that put it all together for 64 carrier waves, various states of the carrier wave to communicate several different 2, 4, 6 bits. And we move to MIMO, which is now giving us the ability to send these signals across 2 polarizations, and thus we could send either the same data on both, combine it on the receiver, and as if it was one, just one polarization, or we could send double the data to double the rates that we could get and receive both uniquely on the receiver. Now I'm going to show a slide. These are the modulation coding schemes. Is the table of all the different how many forward error correction bits, what modulation we're using. And the spec has, in 802.11n, has MCS 0 through 7 is one data stream out both polarizations. 8 through 15 is 2 data streams. They're doubling up on the data. And the spec actually has 3 and 4 polarizations, which is not used in long distance because the polarizations begin to affect each other and interfere with one another, such that we just don't get sufficient signal to noise ratio and improve throughput to try to do that. So we only look in the spec at the MCS up to 15. Signal to noise ratio, that's really king here at these long distances. We have to have sufficient SNR to be able to detect the state of those carrier waves. So the radio is going to try to do double data streams here at all kinds of rates. It can send half the data on one stream at various rates, but it's going to pick the one that maximizes the throughput. Now, there's a lot more packed into this as well. I think there's some good write-up and read the docs about mixing devices with one antenna versus two polarizations, what to expect and what scenarios are the pluses and minuses of mixing those kinds of devices. But really, in summary, you want and should focus on all MIMO two polarization devices. They outperform in a single antenna polarization device pretty much all the time. So don't recommend any single polarizations today. So let's look at this table real quick to go through it. Here's the modulation and coding schemes that are in use, and they define them in the specs with this index from 0 to 15. And here we are with just binary phase shift keying, so that we're just changing the signal into two states. So it's really easy, relatively easy. We need the lowest signal to noise ratio to detect that carrier wave in two signals, two states. Here it is in 4 states, and then we jump up to a 16 state signal, also starting to use the amplitude of it, and then 64 states. And that's all in one polarization. And then if you look down here, then we do the same thing on 2 polarizations. You can see MCS 0 and MCS 8 are the same modulation and coding scheme. The only difference is that they're using 1 or 2 polarizations. So here's how to interpret this coding rate. This says that for every, there's 1 bit of data and the remaining, which is 1 bit of error coding. So half of the bits are to help recover the data. Here it says we have 3 data and 1 coding bit. The fourth one is forward error correction coding. So when you get to the higher rates, here we have 64 states of the carrier wave, and we're sending 5 data bits with only 1 error correction code bit that's going across that channel. So that's where we get the highest data throughput. In this case, 65 megabits with 800 nanosecond guard interval. Now this 400, and we call that the long guard interval, and that long guard interval is something that in 802.11a and G, which is the older Linksys, only supports 800 nanoseconds. When we went to 802.11n, they said, hey, let's add in a shorter guard interval. At shorter distances in your home, we can cut that in half, and we can squeeze out even more rates. So you can see if you can get the short guard interval, it can go from 130 to 144 max and improve the rates that we can get through there. Now, for our long distance links, generally you're only going to see an 800 nanosecond. It's going to try the short guard interval, but it's generally at the longer distances, 5 miles or more for sure, I think, you're just not going to see that this is sufficient guard interval, and that there's more errors there, that it finds it optimal with a long guard interval. So this table will help you to determine what to expect. And note in mesh status, when you see the megabits per second transmit rate that you're transmitting to a neighbor, it's pulling this exact table of what it's set to, but it's reducing the rate proportionally based on what error rate that all the transmitted packets are actually seeing. So you may be on your link at a MCS 15 long guard at 130 megabits per second, but there may still be, 3% error rate of getting data across there. So that would be, it would show in mesh status a 97% of 130 if there was a actual measured 3% packet loss rate. So that's what you see in the mesh status to transmit to a neighbor. Another thing to look at is that oftentimes it comes up with, well, what about adjacent channels, signals on an adjacent channel? The signal spectrum of a 20 megahertz signal, these align right on top of one another, side by side in the channels, and are designed so that to work and be optimal. And you shouldn't expect interference with two 20 megahertz signals right next to each other. They're meant to and were designed that way with all of those carrier waves, the pilots and the other carrier waves that are modulated in a way to minimize those inter-channel interference. Where you could see some interference is if you had an adjacent 40 megahertz. If you were lined up with a Wi-Fi, WISP operator transmitting a 40 megahertz channel, and it was directly next to you, then you should expect some bleed over, because 40 megahertz signal has a little, in 802.11 has more energy. It doesn't taper off as quickly for a 40 megahertz channel. So that's what to look out for with adjacent channels. If it's 20 megahertz signal, you're okay there. But if it's a 40, you're going to get some bleed through there. So let's take it and go to the next slide here. So some of you have, and this has been in the forums, where you can go to one of the AREDN nodes and actually and see how it's selecting the rates that it's using. Now, this is a rate. Every single neighbor has this table. So think about that for a minute. That means that if I have 10 neighbors, I have 10 of these tables, and every packet or every transmission of data, when it's directed to a neighbor, could be a completely different modulation scheme. And on the receive side, all those receivers, they have to be able to detect when they receive something, what scheme's being used here. So there's a lot of data encoding and in pilot information that helps the receivers key on and figure out, oh, this transmission's MCS 15 or it's MCS 8, whatever. And every packet it receives, it has to go through that detection process on the receiver to figure out what's being transmitted. And every other packet I'm transmitting, if it went to every other neighbor, could be at some different scheme and rate. So here's how to read this real quickly. Here is A means that's the best rate to use. B's my second choice, C and D. So it's just order of choices. P is the highest probability of success, but highest probability doesn't necessarily mean highest throughput of data. The end goal here is to maximize how much data we can get over this in transmit. So here's a link. This is on a mountain peak here in Southern California called Pleasance Peak. It's about 4,000 feet. and it's going to Yucaipa over in San Bernardino area, and it's 40-mile link on 5 gigahertz. So these are rocket dishes on both sides. So we're transmitting at the highest possible rate, MCS 15. This is the long guard interval, so 800 nanoseconds. So it's maximizing at 165 megabits per second. And you can see here what the radio's doing. This is how many successes out of how many attempts transmitted directly to that neighbor. And then about 10% or less of the time, the radio will transmit and explore around. It's not going to assume that, for now, the environment changes over time. It's not going to assume this is always the best. So it occasionally starts sending traffic on these lower, backing off. Well, is that one actually better in MCS 14? And you can see we've got 42,000 some successes, about 500 some 500 packets or so were lost in these attempts, but we have higher throughput on MCS 15 here. So the radio is constantly exploring, sending some of the packets on other MCS rates to explore and keep tracking to the environment to ensure that it's always going to send at an optimal rate. So this is a good place to go. Learn. You can figure out how to telnet into the node, and then you would look at this file here, the rate control stats, and in the path name to get to that it's an ID, like a MAC address of that specific neighbor. And then you can look at each of the neighbor stations that are here and look at them to determine what each neighbor, why it's making the decision that it's making to transmit to that neighbor. So yeah, and this is 10 megahertz. Now keep in mind, I'm at 10 megahertz. So when I look at the rate in the rate table, you'll find on the internet, you got to cut it in half because I've cut the bandwidth in half. So it's not 165, it's 82 and a half max rate on 10 megahertz. So okay, and that was the presentation. I see that we have some of the question and answers out there. I would need a minute to absorb those, but I can follow up if necessary here in a few minutes. And I think with that, Orv, unless there's any specific questions in real time right now over the line, I would hand it back to you, Orv.
I think they've been addressed. I will stop recording now.